Okay, so now I will just move on, completing the exact equations, and then moving to substitutions, and probably we will have some examples in your homework that I think I need to mention. Okay, but let me just continue first. Okay, the exact equations, and then next is substitutions. So to complete my lecture, okay, so the exact equations, if you remember that we have, for example, what we are going to do is we are going to find out how we make sure that our equations is exact. Okay? To make sure of that, we are usually, for example, this equation, the last equation we solved, we make into our dy dx, and we have some part of it, right? And we can write this equation as this, okay? And let the equations with dx becomes m, and equation with dy becomes n, okay? And by using the structure in partial, okay, remember the partial derivatives, we can partially derive the m with respect to y. Okay. So when we have 2x plus y, differentiate with y, then it's becoming this one because x becomes a constant and it's 0, right? And the same thing with n, but we partially derive with x and it's become 1, right? Okay. And because it has the same result, then we know that this is the exact equation and we can apply the behavior in partial derivatives. Okay, so we take the integrations. Okay, we take the integration of 2x plus y dx. Okay, because it has the elements that is in the x, right? Okay, so we can integrate that. So we can have x squared plus xy plus a function of y. Okay, that when we derive with partial x, it will be just 0. So we have this. Okay. Now we have this as, let's say we imagine that this is becomes our function xy. Okay. Now our function xy, suppose that we are going to partially derive with respect to y. This is what we have here. And when we are deriving this with respect to y, then it will become just x plus g prime y because x squared becomes 0. Okay. So it becomes this. Okay. Now what's happened? This is actually our n. So it's our n. So we are going to equaling this x plus g prime y with n. N is x minus 1. So this is what we have here. X minus 1 is from n. Okay. So g prime y is negative 1. So we can integrate, becomes negative 1. And don't add any constant here because it's not really that it doesn't really matter. Just be mindful that okay, then we have our f. Okay, our f is x squared plus xy minus y. Okay, and it depends on what questions you have. Usually, if you are given this initial value, then you can plug in the value to check the constant. Okay, to check the constant. So usually the solutions is just let's say f xy equal constant. This is the solution. But if you are given the initial value, then you can find this c. Okay? You find the c, then it's negative 1, and that's the complete answer. So we are going to evaluate. Okay. Or we can solve the equations and make into explicit solutions like this one. That's also. You can have an implicit solution or explicit solution. Depends on the requirements. Okay? If the question need you to write in the explicit form, then you need to write in terms of y equals something. Okay? And I think in the homework, some students may using the explicit or implicit, but I think that's still okay. But be careful, okay? When the question asking exactly need to be like implicit or explicit. You need to be paid attention. You have to pay attention for that as well. Okay. Okay. Another thing. Notice that I start this with m, but you can also do the same thing with n. Okay? You can start with n, and you take the integration with respect to dy, and you have this another. Now it's hx instead of function of y here. Okay? And then do the same thing, but different variables when you partially derive. Okay? And the result is actually the same. Okay? And I have uploaded this note. I just uploaded the note in your folder, drive folder in your homework one. Okay? So if you check out the homework one folder that I gave you last time, you can check the notes. It's supposed to be engineering math, blah blah blah, week one. Okay, so you can check my notes up until here, up until here. Okay, just a quick review of the exact equation, right? Okay, now the problem in exact equations that you might encounter is, for example, if you have so recall that you have m, let's say mxy dx plus n xy dy. Let's say it's equal 0. So this seemingly the exact equation. Okay? So if if the equation, when you try to prove whether it's exact or not, if this equation is not exact, if the equation is not exact, which means the mixed partial is not the same. This one, this is not the same. It's not the same. Okay. If the equation is not exact, then how can you solve this? Okay. Then we we can multiply with integrating factor. Let's say integrating factor, let's say the r x y, or maybe with the red color. Integrating factor. So the equation becomes and then by multiplying this integrating factor, the equations now is exact. Okay, of course, we need to find out what is the integrating factor that can make this whole equation become exact. Okay, so this is called sometimes it's called the almost exact equations. It's almost exact equation. Okay, now what we are going to find out is how we can define our integrating factor for this equation to be exact. Okay, so that's at least the idea behind this the method. Okay, this is also integrating factors in exact equation. Okay, okay, let me continue. Okay, let me write again.
Professor,
Yes.
I think you forgot to record the you record already.
Yeah, already record.
Oh, okay. Thank
Yeah,
you.
already record. Yeah. Yeah, already record. Yeah. Okay. Now, the criteria for equations to be exact. Okay. To remember that we need to find the partial, right? The partial, right? The partial. Let me write. So R M Y, which means that we derive R M which a partial Y. Oh, let me write completely R N X, or this is we can write as R M and partial X R N. Okay, by the product rule, we might have R plus RY M R and X plus Rx N. Okay. The subscript y here means the partial y, right? If you remember how to write the partial derivatives. And we can write down, we simply move the partial. So let me write the part, let me write the green for Rx N minus Ry M, and then R, maybe R My minus Nx. Okay. Okay. Uh, the functions, or m, n, and the partial, they are all known functions of x and y. The problem is how to determine how to determine the Rx, y. Okay, now suppose, okay, the assumption, because if this is function of two variables, we are not really sure on how we can partially derive with respect to x or y. So we assume, so this is also important, we assume, so the assumption that we are going to make is that R is a function of just one variable. Okay, case one, if R depends only x. Okay. So when we partially derive, then though, or maybe green, though x R, based on what we have here, then the other part will be a 0, then we will have my minus nx divided by n and multiply with r, okay, from here, and divide by n here, okay. That's case 1. And if R depends only y, then this becomes r d dy become n x minus my multiply with r. So, okay, for this two, this is what we call the integrating factor, this one. So we have the integrating factor, that is Rx. For this one is e with power my minus nx over n dx. And this one becomes Rx e dy. But to make it more easy to be followed, let me just write for, it's not Rx, sorry. Let's say Ry. Okay, to make it easy to follow, okay, let me just write this integrating factor for the Ry. E, let's just write with the similar form with the x, it's my minus nx, right? Like this. But let me add minus in the front. Okay. So that basically you need to focus on my minus nx. For y, you can just add negative. Okay. Okay, it seems what we have done here, it's not really, it seems not practical, but it's actually practical. So what we are going to do is, when we have an equations that it seems exact, but when you check, it's not exact. The first thing you can do is identify n, and you can take this approach. Okay, you can take this approach, find this, and take into integrating factor, and you need to decide. You need to divide by n or divide by m. Okay. So what's the deal? Okay. For example, if you divide by n, and you are sure that it will be only depends on x. So it's kind of trial and error, and you can see from the equation itself. Okay, the equation itself. Okay, let me give you an idea. Just a quick example. Okay, just a quick example of how we can use this in our solutions. Okay, let's say we have xy plus 2x squared plus 3y squared minus 20. Okay, well, we are not sure it's exact or not, but we can check the exactness. This is m, oh, I forgot the dx, sorry, dx here. Okay, so this is m, and this is n, right? Let's just check. So first is checking the partial, let's say xy, this become just x, and checking partial for the other one, this becomes 4x. It's not equal, right? It's not equal. So what we are going to do, we need to find an integrating factor to be multiplied. Okay. So this integrating factor is not the final result we need. We need this to be multiplied with the equations and make it an exact equation. Okay. So let me just go to the example. So what we're going to do, we are going to find the integrating factor. How? We just focus on finding my minus nx. Okay, so we already evaluate that. So x minus 4x. Okay, notice that this is just resulting in negative 3x. So if you divide either with m or with n, you will find at the later part it will be resulting in only one variable. Okay, now I think it's easy to be observed that m is more simple, and I think it's easy to be defined, right? If you compare with the n, it has plus, and then it's not easy to be divided, right? So this is going to be divided by m, which is xy. So we are going to have negative 3 over y. Okay, and this is our integrating factor. So remember that when we divide by m, actually what we have is the integrating factor in terms of y. So we are going to have an integrating factor that is e integrate negative 3 over y dy, or this becomes e 3 1 over y dy. It's ln e 3 ln y, or e ln y cubed, or we can simply say that this is y cubed. Okay. If you want to follow what the textbook is, the textbook using the nx minus my. But for my case, to make it simple and you can just follow just as it is, just take it my minus nx. Okay. Then later, if you are having y, in your integrating factor, you just need to add negative in the front. Okay. I think it is more easier, more practical, rather than you need to focus on which one is positive, my or nx. Let's just add the negative at the equation and it will be solved easily, right? Okay. So integrating factor is y cubed. What happened after this is, the second step is, so first step, okay, so first, let me write here, first identify m and n, check exactness. If not exact, find r. Okay, find r. It can be rx or ry. Okay, and then multiply equation with r. Okay, that's the idea. So next thing is we need to multiply all with the y cubed. So xy multiply with y cubed, and then the x, and then plus, let me just write one by one, and then y cubed, and then dy. Okay, now let's just multiply as usual, xy with power 4 plus, this becomes 2x squared y cubed plus 3y with power 5 minus 20y cubed dy. Okay. Okay, we can check and verify whether this is exact or not. And we do the same thing as we have done before. So we check this is m, this is n. Okay, check again. So m, we partial derive with respect to y with m, x, y, 4, or we can say that this is 4x, y cubed. Okay, and the n with partial x. Okay, for the other two, this one 0, right? And this one, with respect to x, it's become 4x y cubed. Now it's exact, right? It's exact. So by this multiplying with the integrating factor, we can make the equation that seems almost exact becomes exact, okay? And then you can just follow the usual exact equation. If you want to solve this completely, you can try to take integrations. For example, the x here, so x, y, 4, we can take this. So let this become fxy. So take the integral with respect to x, and we take this as half x squared y 4 plus we have another function here, okay. And then as usual we take the partial y for the f, and this will be 2x squared y cubed. And this is supposed to be equal with this, right? Okay, because it has the same 2x squared y cubed. Okay. Then the g prime y is 3y with power 5 minus 20 y cubed, and we can take the integration with respect to y. Then g of y becomes 6, right? 6 half y 6, and 4 is 5 y 4. Okay. Now the f x y becomes half x squared y 4 plus half y 6 minus 5 y 4 equal a constant thing. And this will be the general solution. Okay. So basically, we combine the integrating factor with the exact equation. So multiply equation with r and then solve the exact equation. Okay. Okay, any questions? Do you want one more example to make it clear? Okay. Okay, one more example. Okay, this is integrating factor in some equation. Let me give you one more example. Okay, one more example. Or do you want to take notes for here first? Okay, I can give you a few minutes for this notes. Okay. Let me check. Okay, let me give you another example. Okay, solve x squared plus y squared over x plus 1 plus 2y dy over dx equal to 0. Okay, let's start. First thing, we can rewrite this x squared plus y squared x plus 1 and take the x here and plus 2y and then dy equal to 0. And as usual, we can check the exactness. We check the exactness. We take this as m, take this as n. We take the partial, and we take partial 2y. This is becomes 0, but this one, this becomes, let me write, x squared plus x plus 1 plus y squared x plus 1. Okay, now the whole thing here becomes 0, right? Becomes 0. And this one, because it's just y, so it's become 2y over x plus 1. Okay. Now it's not exact, right? It's not exact because it's not the same. But we can take and find the integrating factor to find out how can this almost exact becomes exact. Okay. So we take the my minus nx. We just simply write the equation itself, 2y over x plus 1. Okay, now compare with the m and n. How do we decide which equation that we are going to divide with? So the question is, we can divide with m or we can divide with n. So if we divide with m, if you see the equations, well, you end up with a function of two variables. That is not what we want. We want only one variable. So that's not the good idea. So let's just take back. So maybe n. Okay, because when we divide with n, we divide with 2y. So we are going to just having 1 over x plus 1, right? Canceling. And this is just a function of x, right? It's one variable. So we are going to have rx. The integrating factor is 1 over x plus 1 dx. Or we can simply integrate this, become ln x plus 1. And we can simply say that this is x plus 1. Okay, and then this will be our integrating factor. And the next section, the next step is to multiply. So multiply, so x squared plus y squared. So we multiply with x plus 1. And then plus 2y multiply with x plus 1 and equaling 0. Okay, so we have x squared plus y squared dx plus 2y x plus 1 dy. And then we do the same thing. We make it m, make it n. You can check whether it's exact or not, but it's exact. You can check. So we can take the partial partial y. This becomes 2y, and take the partial x off, and you write 2xy plus 2y. This becomes 2y. Now it's exact, right? Exact. Now we can take the integrations. We can take the integrations. Let a functions that is equal, and take the integrations of x squared plus y squared with respect to the x. This has become 1 over 3 x cubed plus xy squared plus g of y. And we need to find our g of y. Then we need to partially derive of our f. Then this will be 0. This will be 2xy plus g prime y. And you notice that this is actually similar to what we have, right? So 2xy plus g prime y is equal to 2xy plus 2y. So the g prime y is 2y, and we take the integrations with respect to y. So this will be, let me write in it here. G of y is y squared, right? And the total equations that we have is 1 over 3 x cubed plus xy squared plus y squared is equal a constant. So this is the implicit solution. Okay. Okay, maybe there any questions that you may be having difficulty now here? So that's the exact equation, and we can move to, after this we can move to the substitution. Okay. Okay, let me just review a little bit what we have here. So the idea first is check the exactness. If it's not exact, but you think that maybe you can do something with the exactness, then you can check whether you can find the integrating factor for it. Okay, if you can find the integrating factor and you multiply and it becomes exact, you can solve with exact equations. Okay, you can solve with exact equations, and then you find out that, okay, this is proof that it's exact, and we can solve by exact equations as we have done since last week, the exact equation. Okay. So the additional part is we can have a multiplying factors in the integrating factors. And how the integrating factor works is the same as when we have the linear differential equations, okay, if you remember the linear dE using the integrating factor, and you need also to multiply, right? This is also works the same. You need to multiply. Okay. Okay, let me move to the next section, which is the substitution. So for the chapter 2, we just left with, so we have learned exact equations. Let me just recap what we have, okay, since the chapter 2. The chapter 2 is the slope fields, the separable equations, linear equations, okay, substitutions, exact equations. So now we still don't have the substitution. We will learn substitution. And also we learn about the autonomous first order, right? First order differential equation. Okay. Now one more for this chapter is the substitution. We will skip the numerical method. We will skip the models. I think in 2.78 and nonlinear models, the linear one, we'll skip all that once. Okay. And after we finish, we jump to the higher order or the second order and higher order. Okay. And hopefully, if we can complete the higher order at least by this week, the next week, that will be our midterm. Okay? And before the midterm, in this week, I can also give you more, not homework, but it's like a test through the online test. So I will give you the link probably on Wednesday, and you can solve it maybe from Wednesday to Saturday or Sunday. I can give you a lot of time before the midterm. Okay? Midterm probably next week, either Wednesday or maybe Monday, depends on our progress this week. Okay. So let me finish the substitutions now. Okay. Okay. Now the substitutions. Substitutions. Okay, if we have that the differential equations that define, let's say define as this function of x, y. Okay. Let's say let y is g of x multiply with, let me just start with the function, this different function of g, x, and with different variables u, okay, where u is function of x. So let's say that's our connections. Now we can take this dy over dx, and we take the product rule of this g, okay, and let's say g can be partially derived, okay, then we can have g of x, gx, partial gx, xu plus partial g with respect to u, xu, and then du dx. This is just a simple product rule. And since we have these connections, then we can exchange this part dy dx, since dy dx is fxy, so we can exchange this. Let me write here. This become fxy, and y itself is g, so we can change that as well. So change the y here. So x and then g, x, u, right? And then this part is g partial x, and then g u x u du dx. Okay. if we try to solve with du dx, the later form, maybe we will have another function f with x, u as its variable. Now, the idea is if we can determine a solution, let's say u pi x, okay. So if we can determine that this is the solutions, then the solution of original differential equations is y g x pi of x. Okay. It seems a little bit complicated, but it actually works similar like your substitution in calculus. It works similar. Okay, but before that, let me just give you another property that probably important in the substitutions, which is we call the homogeneous equations. Okay. So let me give you the property first, and then let's see how we can solve some examples on the substitutions. Okay, if function f possesses property f tx ty t with power of alpha f x y, so we can take out the component t. Okay. This is for some real number alpha. Then f is said to be homogeneous function of degree alpha. Okay, for example, the fxy x cubed plus y cubed, this is we call the homogeneous function of degree 3. Since we have, if we take we can take out t cubed out in the front of the x cubed plus y cubed, and we can say that this is okay. Or t is just the degree of the polynomial degree. And if we have fxy, so this is example 1, example 2. If we have x cubed plus y cubed and we add plus 1 plus a constant, then this will be not homogeneous because of this constant. Okay. So okay. If we think in the first order differential equation. So the first, let me write in the new page, okay, to make it clear. This is the main point, okay, for the homogeneous. So the first order dE in this form, m x y dx plus n x y dy. It's the same what we have in the exact equation, right? So we call this homogeneous if, okay, m and n are homogeneous function of the same the same degree, or we can take this in terms of tx ty to describe the degree. So it's supposed to t with power of alpha m x y, and n also the same. Okay. The homogeneous is a little bit different when we learn the first linear order. If you remember the recall, okay, let me just give you a quick feedback, a recap from the linear one. So if we have a1 y prime plus a0 y equal gx, this is homogeneous when g of x is equal 0. Okay, back to the m. So we can call the m and n. So m, so if m and n homogeneous function of degree alpha, then and the n where the u is y over x. Okay, that's the first one. The second one is we also may have the degree of in terms of variable y. So this is m, let's say v, okay, v1, and for n same is y alpha and v1, and v is x over y. So this suggests, okay, so what's the implications for this homogeneous one? Okay? So implications, it suggests that substitutions that are useful for this equation to be homogeneous is y equal ux or x equal vy. where u and v are new dependent variables. So when we have, okay, so after substitutions, after using these substitutions, what will happen? The homogeneous equation will reduce to separable first order differential equation. Okay. Okay, let's observe of one illustrations, and then I can give you an example on why this happened. Okay, let's say we have m. Okay, let's say we have this, and we can rewrite this a two-way we can write. The first is x with power of alpha m, and let's say we are writing substitute ux, okay, so 1u dx and plus or we can take the y alpha, but let me just focus this one first, okay. Or we can just take simply m1u dx plus n1u dy, and then let the u is y over x or y is ux. Okay. Now substituting the dy is u dx plus x du, right? Okay, from this product rule. Substituting the dy, now we have m 1u dx, okay, plus, and substitute here this dy to here, so plus n and then u dx plus x du. Okay. Now combine this dx, okay, combine with grouping together, so m plus u and 1u, this is dx, plus x and 1u du equals 0. Okay. Now divide with this and divide with x, so, or we divide with the x and 1u plus un. Okay, and this will be dx over x plus n 1u du divided by m1u plus u and 1u. Okay, it seems like it's complicated, but this is just to show you that we might have, when you look on this solution, this is a separable one, right? It's x with x, u with all u, right? So it's separable. So that's how we are actually using the substitutions. Okay? It seems it's not really a practical because I'm not using some functions that is in the examples, but just to show you that when we take the substitution, we can have uh, our homogeneous equations become a separable one. Okay? Let me show you more in more practical way. Okay? So the key for the substitutions to be worked is to define the substitutions, whether it's you need to substitute y with ux or x with vy. So it depends on how the structure of the equation will be. Okay? And also depends on which equation that's simply preferable, easier to be constructed, and which one is not. Okay, let me give you a practical example to let you have more idea. Okay? Okay. If you inspect, this is let's say we have inspections for this one. So we have t squared x squared plus t squared y squared. Okay. So we have the coefficient of homogeneous that is in the degree 2. Okay. This is also the same t squared t squared minus t squared xy t squared x squared, and this is also having 2, right? So degree 2. So polynomial degree 2 for the homogeneous. So let m xy becomes x squared plus y squared, and n is x squared minus xy. So let substitutions of y equal ux. Okay. And we might have dy becomes u dx plus x du. So we may substitute. So x squared plus substitute y. Okay, substitute y with ux squared, and then the x, and then plus x squared. Xy becomes minus ux squared after substitutions, and dy becomes u dx plus x du equals 0. So here becomes x squared 1 plus u dx plus this will be x cubed. This will be x cubed 1 minus u. It's 1 minus u from here, and du, and equal to 0. Okay, now we take the we divide. Okay, we divide and we make that 1 minus u over 1 plus u du. This will be plus, divided by x cubed become 1 over x. Okay, now this is actually a separable one, right? A separable one. We can take both to different sides and take the integrations. Okay? And I think in your homework there are some parts that you need to take some integration of some fractions, right? For example, like this one. I think not exactly like this, but whenever you want to define a fractions, there are several methods that you can think of. Okay, the first one is you can separate the component becomes using a partial fraction, or you can just divide with long division. Okay, what does it mean is we can just take this 1 minus u divide by 1 plus u. Okay, so we take the wait for a moment. Okay. Okay. Oh yes, this long division. So we take the because I want to remove the u, so I will take this -1. So this will be becoming negative u, -1, negative u. So I will cancel the u, and this will be having 2, right? So let's just take this in our integrations of -1 plus 2 over 1 plus u. Okay, du. Okay, this is how you've done it. Okay, so if you, I think a few students they confuse on how to solve this kind of integration. So you can take long division and you can separate this, becomes this, and it's easier to be followed, right? Or you can simply just use calculator to check. Okay? That's the more practical one. And then this will be the ln, right? Ln. We can take this plus c. This is negative u plus 2 ln 1 plus u. Let me just write in this plus ln x equals c. Okay, let's say c. And then the final part is we convert the equations back to the original one. So we take the u is y over x. So we can change all negative y over x plus 2 ln 1 plus y over x plus ln x equal, let's say it's different constant, so let's say it's c2. Okay. Okay, we can stop here, or if you want to write all in terms of in more not in an implicit way, then you can solve through the ln. You can combine the ln if you want. So this will be ln 1 plus y over x squared and then this will be x, and then this will be equal to y over x plus C2. And this will be 1 plus y squared x squared plus 2y x divided by x. We can have ln x plus y squared x, probably like this. Yeah. Or maybe just simply write this, or maybe just this is okay as a solution. Okay. So what's the idea behind the substitutions is you can take substitutions like using y over x with you change with u, or you can take the also y for substitution for v. Okay. So let me just give you this practical use. So you can take this y equal ux or x equal vy to substitute your equations. Okay. And then after substituting, then try to check out whether your equations is separable or not. Okay. If it is separable, then you can finish the separable differential equations, find the solutions, and convert back to the original equations. Okay. So if the solution still have u, then you can check the final solutions, change back u into y and x. Okay. Let me give you another example. So the idea behind the substitutions is if you have this kind of equations here, dy over dx equal x minus y plus 1 squared. It's not linear, it's not separable, right? So we need to find a variable that can substitute all this, becomes a new substitution. And how we substitute is basically we can substitute in many ways. Okay, it's not always using y over x like here, like u is y over x or v is x over y. This is just simply the fact that we are going to have in homogeneous equation, but we can also have another way to solve. For example, this one, we can try to make it out with another substitution. Let's say v, let's say x minus y plus 1. Let's say we have this. Okay. If we differentiate with respect to x, okay, we can take the v prime or dv dx. Let me just write dv dx. This is 1 minus y prime or dy dx. Or if we write in terms of y prime is 1 minus v prime. Okay. Now this becomes 1 minus v prime is equal v squared. Okay. In other words, we can have v prime is 1 minus v squared. Okay. Now we can solve this by separating the variable. So 1 over 1 minus v squared dv equal dx. This becomes, the solutions becomes, we take the, if you check the solutions, we take the integrations for both of this. we can take this half ln v plus 1 v minus 1 equal x plus c, and we can find the v plus 1 v minus 1 and eliminate the ln, becomes e 2x plus 2c. Or we may take another constant. Let's say this is c1, so v plus 1 v minus 1. Let's say it's another c2 e with power of dx, 2x. And remember the singular solutions, we can also have v equal 1 and v negative 1 also as solutions, singular solutions. But we need to bring back the original equation. So take the x minus 1 plus 1 plus 1, x minus 1 minus y plus 1 minus 1. Or we may have x minus 1 plus minus y plus 2, x minus y, c2e power of 2x. Now solving this, we can have x minus y plus 2, x minus y, c2e 2x. So x minus y plus 2 is c2x e 2x minus y c2 e 2x. Okay, let me grouping all together, the y c2 e 2x minus y equals c2x e 2x minus x minus 2, y c2 e 2x minus 1, c2x e 2x minus x minus 2. So we may have y, our final solutions, becomes c2 e 2x minus 1. Okay, now if c2 if c2 equals 0, this gives you y equal x plus 2, right? Because it's 0, 0, negative divided by negative, it's positive. But there are no value of c2 gives solution y equal x. This solutions is actually from here. Okay, this is give you an idea that one of solutions might be the singular one. This is perfectly the same on when we confirm. Okay. Don't forget this, the singular solution, okay, the one that makes your solutions undefined. Okay, that's the singular solution. But seems here, yeah, I would like just to show you that some certain substitutions might work. Okay? Some certain substitutions might work. So you can actually think of many ways to substitute. Okay, not only limited to the homogeneous one that is in here. Okay, so this is for the homogeneous function of the same degree. So you can have y equal ux or x equal vy. So you can have u is y over x or v is x over y. You can substitute and solve the separable differential equation at the end and convert back to the original equation. Okay. And there are some patterns that might work. Okay, let me just give you the practical way to substitute. Okay, let me give you several elements and what kind of substitution you need to make. Okay. Let me give you here summary for substitutions that you might have. If you have y prime using sub of u equal y squared, or maybe phi, okay, phi. When you have y squared y prime, you can sub phi equal y cubed. If you have cosine y and y prime, you can sub with v sine y. And if you have sine, you can substitute v with cosine y. Y prime e to the power of y, you can sub the v with e power of 1. So this will be, if you can imagine what is happening here is basically the way we substitute is you're making, for example, this e with power of y. If you substitute, it becomes y prime v. Okay, this is actually the idea. So when we have this v equal y squared, then we will have y is square root of v. So square root of v, or probably you can check the phi prime. The phi prime is 2y y prime. And then when you substitute, you can have really good structure to be separated. Okay. This is just a summary for some patterns that might work for substitution. But actually, the substitution is not, you can have many ways to substitute, and basically the idea is you need to find a way to substitute and make the equations become separable. And that's the way you look at it. Okay, there is one specific substitutions that we call with certain names. Okay. In our case, it's called the Bernoulli equations, and that is very specific on its structure. So we can call it Bernoulli equation. We may have an example later on, okay, for substitutions for another one. Let me just get through to the Bernoulli equation, and we can have a little bit review on what is substitutions. Okay. This is just some pattern that might work. Okay, Bernoulli equation. So there is a general rule for substitution that is always works. Okay? So we can write the equation as dy over dx plus p of x y equal f of x y with power of n. Okay. So this is called the Bernoulli equations. Note that if n equals 0 or n equal 1, the equation becomes linear. So for n not equal 0 and n not equal 1, substitutions the sub u equal y 1 minus n, it will reduce any equation to linear equation. Okay, what does it mean? Okay, let me just show you quickly here. So x dy over dx, for example, plus y x plus 1 plus x y 5 equals 0. So let me just get straight what we have here. So what we are going to do is we are going to identify. So first is whenever you have dy dx, you have dy dx, right? All right, we can move on, and we see that we have p of x, we have y, and then let me just rewrite. Okay, rewrite the equations as p and f. Okay, so this dy over dx has x. Let's just divide by x. So dy dx plus x plus 1 over x y equal negative y to the power of 5. Okay, now simply we can get this is dy dx. This is p of x, so this is p of x, okay. And this will be, so this negative 1 is our f of x, right? So that's, we can identify that this is Bernoulli equations, identified as Bernoulli equations. Okay. Okay, now what we can do, we can substitute. Okay, we can substitute. So let me write again. Let me write that dy over dx plus x plus 1 over x y equal negative y equal 5. So p of x is x plus 1 over x, and f of x is negative 1. So we substitute this u equal 1 with power of 1 minus n. Okay, so let me write here that u is y with power of 1 minus n. Okay. So n is 5, right? So u is y negative 4. So du or u prime, let me just write u prime is negative 4 y negative 5 y prime. Okay. In other words, we can have y prime is negative 1 over 4 y 5 u prime. Okay. And then using this substitution, we are going to substitute this, but let me write here as y prime plus x plus 1 x y. So let's substitute here. Okay. Or maybe let's substitute the equations that is on the original equation. So x y prime, x plus 1 y, and then plus x y 5 equals 0. This is the original equation. So let us substitute. So x y prime, it's become negative 1 over 4 x y 5 u prime plus okay, let me just write x plus 1 y plus x y power of 5. And let's combine this y5. So this will be negative x over 4 u prime plus divide by y5, divide by y5. Let me just divide by y5. Let's cancel, right? Cancel. And this will be x plus 1 y to the power of negative 4 plus x equals 0. And then this is y negative 4. This is our u, right? So we can exchange this to u. So let me write with different color altogether. Plus x plus 1. This is u plus x equals 0. Now we have a variable of u and x. Okay, and we can try to find out how maybe we can separate this. So let's just maybe take the negative 4 over x. Maybe we divide with this. So u prime negative 4x plus 1 over x u, and this will be negative 4, but let me write in equal 4. Now instead of separable, we have the linear differential equation. Okay. And suppose that the initial conditions is at 1 1, which is in the positive terms. So assume x is positive, so all the absolute value will just equal to x. Okay. So we may compute the linear differential equations, and remember that this part here, the negative 4 something here, this is going to be our p in linear differential equation. So we can find the integrating factor, that is e. Let's say we are having p of x, or here's the, let's using the variable s. Okay, and e let x equal 1. Okay, and we compute the integrations from 1 to some x, and put just at our integral defined value here. This is negative 4 s plus 1 divided by s dx. So e negative 4x, negative 4 ln x plus 4. Okay. So this is e negative 4x negative 4 ln plus 4 and x negative 4. Okay. Okay, I'm turning this into x minus 4. Or we can write, yeah, it seems complicated, but just check it first. Okay. Now we have ux. Now we plug in the formula. Okay, that we have. Let me just write this. That we may have 4x minus 4x with power of 4. This is from the e negative 1x p of x dx. I think the example is not really perfect and ideal, but let me just write here e okay, wait. I think not really good way to. Okay, let me just give you another example to show you a better way to solve. Okay, better way to solve. Okay, wait. Okay, I think this is not really. Just clear the page. Okay. Let me just change the equations. Okay, change the equations. This is not really an ideal way to introduce the Bernoulli equations. It's too complicated. Yeah, let me give you the easiest one first. Okay, I think this is better. Okay, we have dy dx, we have y, we have f of x, y with power of n, right? So we can describe this in terms of Bernoulli. Okay, this is the Bernoulli. This is n equal 2, so we can substitute. So sub y equal u negative 1. Okay. So 1 minus 2, right? Okay, and then we have dy dx or y prime is negative u negative 2 du dx. Okay. So this is the one that we are going to substitute. The next is we are going to substitute. Let me write the dy dx is negative u negative 2 du dx. and u is u negative 1. So we can exchange, let me write the original equations. Okay, let me exchange this. Y is u negative 1. Let me check. X u negative 2, right? And we can divide all with u negative 2 and change the signs. This is the u dx minus 1 over x u equal negative x, right? This is multiplied with, okay, now going for linear differential, linear first ODE. Okay. Now we are using this 1 over x as our integrating factor, or let me write this is our p of x. So integrating factor r is e with power of negative dx over x, or this will be e with power of negative ln x, or this will be equal to 1 over x. And again, in linear, we are going to find the product form, that is 1 over x and u, because this is perfectly defined here, right? Let me check this 1 over x, du dx 1 over x, this is supposed to be negative 1. Okay, integrating, so integrate, this will give you the 1 over u, let's say u over x equal negative x plus a constant, and this will be negative x squared plus, let's say, c1 x. Okay. And remember that y or u is y with power of negative 1. We have y is 1 over u, right? So the solution gives, this is 1 over y. So y is 1 over cx minus x squared. I think this will be better to understand in compared with the previous one. Okay. Okay, the Bernoulli equations means that whenever you find you have dy dx, you have y squared. Basically, these equations can be simplified into linear differential equation that we have learned before. Okay, so we substitute. Okay, so the idea is actually not that complicated. The idea is we have this some squares here. We want to make this squared or any power to make just a linear. Okay, and how to do that is we are going to substitute with some relations, right? With some relations that when we substitute, this squared will be gone, or reduce. Okay, reduce. And when we reduce that, because we simply have, so we have y squared, and y prime. Okay, so what's the deal with this? Okay, if you connect all these things here, so if we have this y squared, if we take this as our y squared, if we take the differentials implicitly, this will becomes y prime, right? So we have y, right? So basically, what is Bernoulli equation tell us, if we have y squared, y prime, we have some connections to make the equations becomes a linear first order differential equations. That is the goal. So Bernoulli equations, the goal is to make the equation becomes first order, okay, linear. And when you have linear, you can solve by multiply with integrating factor. Okay, multiply with integrating factor and make it the make the equations multiply with the integrating factor, integrate, and then that is your solution. Okay. Maybe to make it clear, I'm skipping some process here. Let me make it more clear. So we multiply u dx with 1x minus 1 over xu, and then multiply with 1 over x, and this is also multiply with 1 over x. Okay. Okay. Okay, I think this example is better than the previous one I showed you. I think this. Okay, the idea of Bernoulli is substitution and make it the first order linear and solve with the integrating factor. You find the solution. You integrate. You multiply with the integrating factor, integrate, and just like first order linear. Okay, maybe a little bit recap for the substitutions, okay, to make it to make sure that we are understand what it is. Okay, so substitutions basically for homogeneous equations, and I think to make it maybe simpler, we are just maybe focusing on this homogeneous one to make it easy to follow. But for homogeneous equations, if you want to make it, uh, if we have the equations, if you want to substitute and we want to solve and make it into separable equation, then if you look at what we have here, this is proven that we may take the substitutions. Uh, for example, if we substitute u as y over x or as v as x over y, it depends on situations. It depends on the equation, which part that it seems that easier to be substituted with y over x and or with x over y for u or v. Okay. Now, the idea behind the homogeneous that use substitutions is every time you do the substitutions, the results will be separable differential equations. Okay. Now, what I have here to show you, okay, this is just one example here using y over x. What I have done here, it's another way. If, for example, if the functions is maybe not homogeneous or maybe in another pattern, you can also check with another substitution that can have that can be possibly done. For example, this substitute using x minus y plus 1. Okay, that's also one way. Okay, one way to solve. But the pattern here is actually some pattern that might work, but for homogeneous. Okay, for homogeneous. Okay. Let me write here for homogeneous. Okay, for homogeneous. Usually we just stick to this or this, and you can just maybe focus only for homogeneous, I think. And another way, okay, aside from homogeneous using substitution as a solution, another way is the Bernoulli equation. Okay. We are using the substitution for this equation here, and we make into the linear the first order linear differential equation. Okay. And how to substitute is basically substitute. It depends on this n. Okay. So you have u, y, 1 minus n. Do you know why this substitution will work? Because, as I mentioned before, if we have y squared, then it will work with this u with power of negative 1. If we have y cubed, it will work with negative 2. Because if you differentiate, it will canceling the other part, and when you solve it, it will be made into linear differential equations. Okay? So that's why this u 1 minus n it's always work. It always work for Bernoulli equation. It always work and makes the equations become first order and linear. It always work. Right? But for this one, if you remember the original equations is x y prime plus y x squared y squared. If with for y equals 0, this is also a solution, right? Also a solution. This is a singular solution for this equation. So this equation is one of some solution that can have. We haven't yet confirmed that this is the general solution because we also have this y equals 0 as a singular solution. Okay. Okay, maybe questions. If you have any questions, or uh which part you think you need more idea. Okay. I think one more small sections uh, regarding the substitutions that I can give to you. Okay. Let me give you some examples. Let the dy dx is equal of function of ax plus by plus c. This differential equation can be reduced to equations with separable variables with substitutions. U equal ax plus by plus c. B is not 0. This is actually example that I have give you this example here. But let me give you the idea and another example to be followed. So example, so we have initial value of that. Okay, now the idea behind what we have here is whenever we can have like imagine that this is another polar function that is having a square. So the idea is making this inside of the functions is the substitution itself. Okay, so let the u is negative 2x plus 1. Okay, so when we have the u du dx, okay, we have negative 2 plus dy dx, and we may transform our equations becomes du dx plus 2 equal, this will be u squared plus 7. Okay, I think it's more easier to handle, okay, rather than we handle this squared with the x plus y inside, right? So when you have this u squared plus 7, it's easier to follow. And we may have du dx. Oh, sorry, it's not plus 7. It's supposed to be u squared. Oh, it's supposed to be minus. Okay, u squared minus 9. Okay, now we can take this du u squared minus 9 equal dx, and we can integrate. Okay. Now again, this is something that I think might appear several times for a while in differential equations, that you need maybe a partial fraction to solve. Right? So let's factor this out. Okay, and we can make so we can have a partial fraction and find a constant. So a u minus 3 plus bu plus 3 is equal 1. So au plus bu minus 3a plus 3b is equal 1. So a plus b, so negative 3a plus 3b is equal 1, and a plus b is equal to 0. So let's just plus and multiply by 3. So 6b is equal to 1, b is 1 over 6, a is negative 1 over 6. So this will be, or maybe let me write 1 over, or 1 over 6 u minus 3 minus 1 over 6 u plus 3. Okay. And this will be du and dx. Can have 1 over 6 okay. I think we can integrate now. Integrate. 1 over 6. This become ln, right? This is also ln. And we can combine this logarithmic. So u minus 3 divided by u plus 3. Okay. And equal x plus constant. Okay. Now this becomes u minus 3, u plus 3. Sorry, this is supposed to be ln. So ln, this is 6x plus 6c1, and u minus 3 u plus 3 is e. Okay. Or let me write c2e 6x. Okay, right. Now apply the initial conditions, that is, we have here. So we may have let me just write the constant, just c e to the power 6x. Solve a little bit. Okay, solve a little bit. Okay, that's our u, and our u is basically, what is our u is negative 2x plus y. So y is 2x plus all this stuff here. So let me, sorry, can you write here? But this becomes this. Okay. Now apply the initial conditions 0, 0. So 0, 0, 0, 0. So 0, 0 plus 3 plus 3c, 1 minus c, right? So 3 plus 3c is 0. So c is negative 1, right? C is negative 1. So it gives the solutions is y 2x plus 3, 1 minus e6x, 1 minus e6. Okay. Okay. The substitutions part, I think the most important here is the first one here. From this part until this one. This is, I think, most important one. Okay. The rest of what we have here is just using this calculus, separable differentiation calculus, and make it into y equals some equation of x here. Okay, the way you look at here is, this is another, okay, so you move from here, going here, and some partial fractions doing by this part, sub integrations, simplifications until here, and I'm writing back this part into here, and then solving these equations and make it into u equals something. Okay, and then u turn back to this negative 2x plus y, okay, and write in terms of y, and we still have a constant, and we use this 0, 0 point, okay, 0, 0 point, and put in 0, 0, and it is becomes a 0, 0 plus 3 plus 3c over 1 minus c, but it's equal 0, so we just simply said that 3 plus 3c is equal 0. So c is supposed to be negative 1 to make the solutions complete. Okay? So we plug in negative 1 to this c here, so we can have a negative, negative. Oh, not negative, this is become positive in 1. Okay. Any questions? And that is the believe is substitution. Okay, and I think for this chapter I will just stop until the substitution. So we have the separable. I think the first one we have the slope field. The slope field's autonomous order, right? Autonomous order, um, separable equation, linear differential equation, exact equation, solutions by substitution. Okay. So five, at least five parts. And the next part is the higher order. It'll start from the second order. Okay. Okay, any questions? Okay, if not, then uh, that's the first order differential equation. I think this week we'll start giving you the first quiz. Probably Wednesday night. I will give you the link and you to check the link. Okay. And I will give you some instructions on how you are doing the quiz. Okay.
Professor,
Yes.
is the quiz involving high order?
The quiz is just the first order one. The first order.
Okay, thank you, Professor.
Yeah. Okay, let me start the higher order differential equation, and we start from the 3.1, the theory of linear equations. Okay, but let me start with the second order. The second order to give you a much more definitive equations to begin with, and you can visualize the equation with some practical equations. Okay. All right, let me start with the second order linear ODE. Okay, consider the general forms as our second order linear equation. Okay. And sometimes we divide and exchange this with 1 over, multiply with 1 over ax to give you much more clear y double prime here. And bx, let's say we are going to exchange to another function of x here. This is also another function of x here, and becomes another function here. So we know that the px is p of x divided by a of x, and q of x is c of x divided by a of x, and f of x, the small f, is the capital F divided by a. Okay. Remember, linear, the equations not having any power or uh, equation not having any powers. I think that is quite simple enough to understand. Especially remember that the objects that we are going to observe is y, y prime, y double prime, etc. So when another case, if you remember, when we have f of x is 0, we call this is homogeneous, right? Homogeneous. So y double prime plus p of x y prime plus q of x y is equal to 0. Okay. The first part is the existence and uniqueness. Let me start with the second order, and I give you the general form for the higher order. Okay. So consider this consider P, Q, F are continuous functions on interval I. And A, B0, B1 are constant. So equation y double prime plus p of x y prime plus p of x y equal function of x has exactly one solution y of x, okay, defined on interval I, satisfying initial conditions, that is y of a equal b0 and y prime a equal b1. So wait for a few. Depends on what order we have in the equation. We will have the solutions when we have the certain initial value, okay? Certain initial condition. Okay, this is the second order. Now, if you look in more general form, okay, let's say for linear DE, we want to solve. Let me write in more construct way. You can have much like more and more high order. Okay. Then we need to have some certain of initial conditions to solve the linear DE. Okay, the first one, if we have this whole thing here, it's an order, okay, differential equation. Then we need to have some certain initial conditions, depends on the order of the linear differential equation have. Okay? So y n minus 1 x0 equal y n minus 1. Okay, so it can have as many as it can be. Okay? It depends on the order, right? Okay. Now let an minus 1 and a1 x a0 x g of x continues on interval I. So this is a more general idea for the theory of the linear. Okay. And let the a and x is not 0 for every x in interval. So if x equal x0 at any point at interval, then solution y of x of initial value problem exists on interval I and unique. Okay, so what does it mean? Okay, if you think this quite have a lot of words. So this is basically what we say if example. Okay, we have 3y triple prime plus 5y double prime minus y prime plus 7y equals 0. So consider that this is a third order, right? So for the DE to be solved, need 3 initial value condition or initial value problem. Or let me write, it needs to be at least 3 initial conditions. So for example, if we have the initial conditions y1, y prime 1, and y double prime 1 equals 0, then we can solve the equation. Okay? So when we have this 3y double prime plus, let's say we are going to solve this, okay? And I think the only solutions that make sense, the trivial solutions is y equals 0, right? So this is the only solutions that can be done. So only solution when x is equal 1, right? When x equal 1. Okay, another thing aside from this initial value problem is we call it the boundary value problem. Okay? The boundary value problem. So let me give you the boundary value problem. Let's say we need to solve the differential equation. Let's say we have the second order. Which is subject to, we have two initial conditions. But we have different x, okay, right? So we call this 2-point boundary value problem. Or simply we call this BVP. So we have IVP, initial value problem, so we have BVP, boundary value problem. And this is called the boundary condition. Okay, let me give the okay, let me copy the file first. Okay, let me wait for a moment. Okay. Okay, now so the solutions, okay, the solution a function that satisfy the DE on interval, let's say interval I, contains A, B, which the graph pass through a y0 and b let's say y1. Okay, so the other pairs, of the BC is boundary conditions. So the other pairs is we have y prime a, that's possible, y b equal y1, y a, y0, y prime b, y1, and y prime a and y prime b. All these boundary conditions. So the solutions that might have is, you see the figure, if we are looking at the x-axis, we may have this line that pass through the equations. Okay, this is just illustration of what we have. Okay, so we have here, we have here. This is if you a family of solutions. So we have probably goes around like here, or goes around here. Okay, that's still possible. That can be a solution. So the solution will be the function that satisfy of course the differential equations, and they contain the point a b, and the graph, they will pass through these points. Okay, and what y prime means, again, this means the slope. Of course, it goes the same point as the graph. Okay, as we can see from the graph. Okay, so back to here, y0 and y1 is our arbitrary constant. Okay? And all the pairs from what we have here, okay? So all the three pairs of our boundary conditions are general boundary conditions for a1y a plus b1y prime a c1 and a2y b plus b2y y prime b, sorry, equal c2. So this is the more general way to see all these three pairs that can be in the functions. Okay. 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 I think I will just stop until here. Okay. And let me check. I think I will stop until here. This is just an introduction, okay, on what we have and how a typical general solutions for higher order can be. Okay, we can later discuss more in afternoon sessions. Okay, so I think I will just stop until here. I will give you a little bit feedbacks for our previous chapters, maybe in the next session. in the afternoon session. Okay. Okay, I think that's all for this morning session. Is there any questions first? The important one for this morning session is for the exact equations, you can have an integrating factor if you are almost exact. Okay? And the second one is the substitutions. And substitutions can be also rewrite in terms of specific equation we call Bernoulli equations. Okay? So we sometimes getting substitutions make it a separable or linear differential equation in Bernoulli. Okay? So that's the recap, at least for this morning. And this one is just introduction on second order and higher order differential equation that we are going to observe more later in the afternoon session. Okay. Oh, okay. Any questions?
Professor, I want to ask, how do we can choose the method that we can use, right? It's
Yes.
not
Yes.
like
Yes. Yes.
one
Yeah.
function only use one.
Yeah. Yeah. Sometimes we can choose which method we are going to solve. Okay. Maybe some method will be easier, some will be difficult, and also to make sure that you are understand the method, understand how to identify whether the method is work or not. You can identify first. I think that's also one key point if you want to solve most differential equation problem. You need to identify first what kind of order you have and what kind of structure in equations you have. And after that, you can simply solve using any method that you can think of, and it's within the requirements for the method. Okay, I think that's all for today. The Moodle still not work yet. I'm not sure when, but it's already been including in the summer course Moodle in the Moodle. So we need to wait because I haven't yet um, assigned in the Moodle system. So it's just updated. It just appear in the Moodle our course, but it's not yet added the students and the instructor. So maybe we need to wait a few days more few days. Okay. And in the meantime, don't forget the folder files that I gave you the link for the homework. I think we will use all the files. Like maybe if we have homework 1, homework 2, homework 3, we are going to use the same link. You just need to find which folder you are going to have. Okay. Okay, I think that's all for today. I will stop the recorder and we may have